Given in this question is, as in this question, there is an ice making plant where the water, first of all, is at 0 degree centigrade, then is frozen by evaporating saturated R134A liquid at minus 16 degrees centigrade, and then the refrigerator leaves this evaporator at a saturated vapor where is also 16 degrees centigrade, and the plant is sized to produce ice at 0 degree centigrade at the rate of 5500 kg per hour. So that means the rate of a mass of W is given, that is 5500 kg per hour. So what we have to determine, this is all the given data. So we have to find out the rate of entropy generation. We have to find. So here's our solution start. First of all, we take the control volume formed by the R134A evaporator with a single inlet and a single exit as the system. So the rate of entropy generation within this evaporator during this process can be determined by applying the rate form of the entropy balance on the system. So the entropy balance for this system can be expressed as like this. So the rate of a net entropy transfer by heat and a mass plus the rate of entropy generation, that equals to the rate of change of entropy of the system. As the system is of steady flow, so this equals to 0 because of steady flow, and this equals to the rate of a mass of m1 into s1 plus rate of mass m2 s2 plus q dot in divided by tw, that equals plus the rate of entropy generation, so this equals to 0. As we have to find out the entropy generation, so this equals to m dot r s2 minus s1 minus q dot in divided by tw. So our entropy generation, the rate of entropy generation, m dot r into sfg, where s2 minus si is equals to sfg. So this equation becomes like this, which we used earlier, later. Now we take the values from table A11, the properties of the refrigerant. So our HF at HFG at minus 16 degrees centigrade is 210.9 kilojoule per kg, and our SFG at minus 16 degrees centigrade is 0.81729 kilojoule per kg into Kelvin. So this value we get from the table. Now as the rate of that must be removed from the water in order to freeze it at rate of 5500 kilojoule per hour. As this condition is given, we discussed earlier. So here we use this formula for this. Now putting their values, as we have to convert the kilojoule per hour into kg per hour into kg per second. So we divided by 3600 and HIF value is 33.7 kilojoule per kg. So this equals to 509.8 kilowatt. As where the heat of fusion of water at 1 atm is 33,333.7 kg per kilojoule per kg. So the mass flow rate of R134A is, our mass flow rate of R134 is Q dot in divided by HFG. As Q dot in, we find the heat of a fusion at 1 atm, that is this. So we find the value of 509.8 kilojoule per second, as watt can be written as also kilojoule per second, where HFG is 210.18 kilojoule per kg. Kilojoule per kg. So this equals to 2.426 kg per second. Now substituting all these values in the formula which we have find of the rate of entropy generation, this formula we have to put all the values in it. So m dot r sfg minus q dot in divided by tw. Now putting all the values in it, that is 2.426 kg per second, and SFG. So SFG value is 0.81729 kilojoule per kg into Kelvin minus 509.8 kilowatt divided by 273 Kelvin. So this equals to 0.115 kilowatt per Kelvin. So this is our required answer, means the rate of entropy generation. So thank